everyone. Today we're talking about the basic building blocks of the op-amp and what are the characteristics of each of these blocks. Uh, think of these things like it has got different blocks and each block contributes to certain characteristics. So think of like I'm preparing a food. Let us first have the requirements or the instructions how to prepare the food. Then we'll go get some groceries or the ingredients. Then we will construct or build the op-amps. Then we will prepare the op-amp. Op-amp has broadly classified as three stages. It has got number of stages, but just for the study purpose at this point of time, just consider stage 1, stage 2, and stage 3. What it should have. Op-amp should have very good. It has two inputs terminal V1 and V2, and it has got one terminal. It is called V out, and it is actually powered by VCC with the negative voltage as VEE. So this particular first stage of the op-amp is called the input stage of the op-amp. It has a very unique characteristics. Op-amps should not draw more current. That is the unique characteristics. So that means it should have very high input impedance. I call it as input impedance. This is first one. Second recipes that are the instructions for any food which I am preparing. Think of that op-amp is the food which I am preparing, which needs to have what is called as a voltage gain should be very high. Current gain should be very high. These are some of the characteristics which I am expecting. Secondly, in the second stage, what happens is that the amplified the output of this stage one will always be drifted away from the baseline, which may be not exactly the baseline of 0 volt or the ground level. It would have drifted away from the baseline. So it is always required to bring this output stage back to the baseline. Therefore, this stage is called as we need to have a level shifters to bring the output back to the zero level or the ground level. The output stage one is something like we call it as output stage. The stage three is called output stage, and this is required to drive very good output swing. So obviously, we need to have a very small difference of the very small input. So I need to have what is called as a very big output. So the swing must be very good at the final stage. If you want the swing must be dynamic or very good swing, definitely you need to provide a very good current to have the good swing. That means the output resistance is low, resistance or impedance must be low, and this should provide very good current for a good swing. The basic thing is that it should not draw more current, but at the output stage, it should be possible to drive very good current. The output stage, you think of it something like you have to drive a very good speaker. You need to have very good drive from the output stage. So these are the basic recipes that we talked about now. Let us understand the stage one at this point of time. What is stage one? So this is called as the input stage. We told that high input resistance and high voltage gain and all those things. Where do we get those characteristics? So let us now understand the the basic structures of the transistors, the basic configurations of the transistors. There are three basic configurations of the transistor that's called common base transistor configuration, common collector configuration, and common emitter configuration. So this is the one. Let us not go into the details of each and every configurations. Think always that this common emitter configuration, which provide us the very high input resistance uh, and and the voltage gain, and the voltage gain and the current gain is high. So can we go on now? We have to buy the ingredients, right? So which ingredients can I buy it now? In order to construct the op-amp, I have to buy this common emitter configuration. So how does the common emitter configurations looks like? The common emitter configurations looks like this. This is RE1. This is Q1 transistor. This is VCC. This is nothing but your RC. This is base one we can consider. I will take the similar one more configuration here. Similar common emitter configuration. This is called RE2. This is called B2. And this is VCC. And here minus VEE. So we have to arrange these two in such a way that we're going to get a uh, two-port configurations or a common emitter configurations. I will I will make some rearrangement of this one. I will join these two in if I can join these two REs, these configurations. Let us rearrange. Let us rearrange these two signals, these two configurations in this way. So let us take this, let us connect these two. Now what happens? This is nothing but your V minus VE. This looks parallel, so I don't want to, I can even just join this and I don't have to, connect like this. I can join this and here minus VE, and this is nothing but your RE is equal to RE1 parallel RE2. So this is nothing but your Q2 and this is RC and this is base 2. Of course, I'm going to have the input signal V1. This is called V2. I'm trying to ground this, okay? And I can combine this VCC. We don't have to just trying to, connect. I am trying to make it one single circuit like this. This is what is called as the, sorry for this, not a good drawing here. So now this is what is called as the difference amplifier. How do you get for the first one, for the first section of this particular one, we are going to get the output from the collector side. I call this as V1. From the second set, I will get the output, which is called as the V2. If I take the difference of the V1 and as well as V2, I call as V naught. This V1 is with respect to your ground. And V2 is with respect to your ground. And the V naught is nothing but the difference between V1 and V2 is nothing but your output voltage. So instead of this V1 here, can I rearrange a little bit here? Can I rearrange a little bit here? It is nothing but this is V1, one terminal, another terminal. I'll bring it over here all the way. So this is nothing but your V2, some base. Yeah. Now, this is V2 signal and this is V1 signal. What does this V1 and V2 is nothing but the difference of the V1 and difference of the V2 will give you V0. So that's why it is called as differential amplifier. Now, the next recipe, the first recipe is done. This is the first recipe. I'm going to buy this actually first recipe. That is the CE configuration. That is the common emitter configuration blocks arranged this way. The second one, let's go to the second one now. That is called the level shifter. The first one is the differential amplifier stage. Output stage is a little bit amplified. I'm showing you only one stage here, but actually it will have um, one more stages. That is the intermediate stage, we call it as. That particular stage, the output actually here, it would have drifted up. I would say that the DC voltage gain is more. It is not at zero level. So we cannot have the output voltage which is above the baseline or the zero level. So what we need to do here is that we need to bring in what is called as a level shifters. Level shifter is nothing but your a two resistor network that we have shown already like this in our previous videos. So the better way to represent actually you also can have a common emitter with the common emitter with voltage divider network. This is the output. Okay. So this output stage you can connect it to this particular level shifter where this is connected to VCC and this is minus VEE. So now what happens here is that we have the differential amplifier and we have the level shifter. What is the final one? Final one is nothing but your output stage. What is the output stage? Output stage is nothing but you want to drive more current for the more swing. That is only possible through what is called as a push-pull amplifier configuration. So what is a push-pull amplifier configuration? It is something like two transistors. One is NPN and one is PNP. So which are connected this way. So those inputs are driven by here. So so this will drive the, let us say, um, this is actually it. This is a capacity to drive the load. At the same time, this has got a capacity to sink the load current. So what happens because of that? So the swing will be even for a small swing. Let us say that you have a positive swing, you will have a good voltage, or I would say that a good positive swing here. For the negative swing, this is responsible for this one, which poses across this RL, which will give a positive swing. At the same time, in the negative half cycle, there's a current sink actually happens that will also drive a negative sink. So it has a good positive and negative sink actually. I'm exaggerating here. Let me write it very clearly. So for the positive half, the upper portion or the upper circuit will take the good swing, and the for the negative of the lower portion of the transistor will take the negative swing. So this happens in the fashion push and pull. So that's why the configuration is named as push and pull. Now I have purchased, this is the output stage push pull PP amplifier, push pull amplifier. Three varieties of ingredients I have purchased it. So, so let me do one thing. I'm going to, add, mix it up everything, and I will make the output will go, this output will go, and you will get a swing like this. This is the output V naught. This is nothing but your V1 and V2. This is nothing but your complete op amp. So here, this is actually we wanted to discuss about the basic building blocks of the op amp. Every stage you can just say this is the first one, stage one, and this is the slice it if this is stage two and this is stage three. In the actual scenarios, the structure of these transistors are pretty complicated. You will have one more intermediate stage which will boost up the voltage levels, and I have not shown here. Let us understand only the differential amplifier thing, level shifter, and the push-pull amplifier, which will responsible for the different characteristics like it will have high input resistance here. Since it is driving a very good swing here, it should have the good I would say that low output resistance. In ideal case, we call it as zero output resistance, but practically there will be little output resistance here. So input resistance, good voltage gain, low output resistance. These are all, the zero output resistance, I would say that. And if we consider the AC applications, so we need to think about what are the characteristics with respect to the AC. For example, if you just look at the bandwidth, it's infinite bandwidth, and it's the bandwidth is very huge. That means it will cover very large frequency spectrum. That's what it says, but practically it won't. It will have a very less, I would say, the predetermined a frequency spectrum. I think this should be good enough. We'll talk about the more of the different characteristics in detail in the next video. Thank you very much.